Bismillahirrahmanirrahim. Assalamu alaikum. Dear students, welcome to the Electrical Engineering channel. In this lecture, I will continue my discussion on application of Ampere's law, and I will apply the Ampere's law on a closed path in which the magnetic field intensity at a point is given as H naught, and around this point, I will have four differential lengths, and those four differential lengths actually constitute a closed path, and I will apply Ampere's law on this closed path, and at the end the expression that I will get is actually of a very important aspect, and that expression will be correspond to the curl, right? So I will demonstrate curl actually in this lecture, and the expression for curl will be derived at the end of this discussion. So at this point, I have the magnetic field intensity as H naught, and H naught is equal to Hx naught Ax plus Hy naught Ay plus Hz naught Az. And let's apply Ampere's law on these four differential lengths. And H dot delta L from path 1 to 2 is equal to Hy from 1 to 2 multiplied by delta y. Okay, so dl is equal to delta L delta y from path 1 to 2, and h from 1 to 2 is equal to hy. So h will have only y component because this path is along the y axis, so hy from 1 to 2 multiplied by delta y, and hy from 1 to 2 will be equal to, so here we have the y component of magnetic field intensity as hy naught, right? So the y component of magnetic field intensity at this point is hy naught. So this is the magnetic field intensity at this point, but when we move away from this point towards this differential length from 1 to 2, we will have to apply Taylor series, and from this point up to this point, the variation in magnetic field intensity will take place with respect to the x-axis, because from this point up to this differential length we have x-axis. So partial hy over partial x we will have, and the separation between this point and this differential length delta y is equal to 1 by 2 delta x, right? So this whole length is delta x, and this is equal to delta x by 2. So that's what I have written over here, and these are the first two terms of Taylor series. We can further expand our expression up to third or fourth um, powers, but those terms are very small and they can be neglected without any problem. So we will consider only the first two terms, and these are the first two terms of the Taylor series. So we can substitute this value of hy from 1 to 2 in this expression, and h dot delta L from 1 to 2 will become this is delta y, and hy from 1 to 2 is equal to this expression. Similarly, we can perform the same operation for the other three paths, and h dot delta L from 2 to 3 will be equal to minus hx naught plus 1 by 2 delta hx divided by partial y into delta y into delta x. Okay, so from this path we will have delta x equal to minus um, delta x, right? So from path 2 to 3 it is actually minus delta x, and this path from 4 to 1 is equal to delta x. So that's why here we have minus delta x, and we will consider the x component of the magnetic field intensity, which is hx naught at this point, and from this point up to this point the variation is taking place with respect to the y-axis, so partial hx naught over partial y will be written over here, and this negative sign is due to the opposite direction of this delta x with respect to x-axis. Similar procedure can be applied for implementing Ampere's law for this path 3 to 4 and for 4 to 1, and we will have such expressions h dot delta L from 3 to 4 and h dot delta L from 4 to 1. So by adding all these expressions, we will have h dot dl over the closed path, and from here we can see that this hy naught will be cancelled out with this minus hy naught, and this minus hx naught will be cancelled out with this hx naught, and at the end we will have partial hy over partial x, minus partial hx over partial y, and this delta x delta y, and here again we have delta x delta y, so they can be taken as common. And this expression is actually the result of application of Ampere's law over this closed path, and this is delta x delta y, and we know that this is equal to delta s, which is the differential surface area. It means this expression is equal to the volume current density. The reason is that we know that h dot dl closed line integral is equal to the current, and this expression is equal to current, and here we have the surface area. It means this thing is equal to current density, because current is equal to j dot ds. So this is equal to j, and this is ds, and ds is equal to dx dy, and the unit vector is az, and this is actually j, so j dot az will be equal to jz. So this is the z component of the volume current density, and this expression is equal to jz delta x delta y. So this Ampere's law has been applied on this path, and this path actually lies in the xy plane, right? So we can apply this Ampere's law for the yz plane, and we can also apply Ampere's law in the xz plane, because here we have applied Ampere's law in the xy plane, right? So this is x and this is y, this is y and this is x. So if we apply Ampere's law in the yz plane, h dot dl will be equal to this expression, and that will be equal to jx delta y delta z. And for the application of Ampere's law in the xz plane, we will have this expression, and that will be equal to jy delta x delta z. So we can add all these three uh, components of the volume current density, right? So by comparing this equation with this, we know that jz is equal to this expression, jx is equal to this expression, and jy is equal to this expression, and the total j actually can be written as the sum of all these three components. So j is equal to jx ax plus jy ay plus jz az, and we can add all these three components of the volume current density j. So this expression we will get at the end, and this expression can be written in the form of this determinant expression. So here we have ax ay az, and these are the components of the vector operator del, and these are the components of magnetic field intensity. So it means j is equal to cross product of vector operator and the magnetic field intensity. So j is equal to del cross h, and if we take the cross product of the vector operator with any vector quantity, it is called as curl of that vector quantity. So del cross h is equal to curl of h, and j is equal to curl of h, or j is equal to del cross h. This is also called point form of Ampere's law, because we have used Ampere's law as the starting point of this derivation, and the expression which we get at the end is actually the point form of Ampere's law, and this is called integral form of Ampere's law. I is equal to h dot dl closed line integral. This is called integral form of Ampere's law, and cross product of vector operator del with vector field is called curl of that vector field, and this curl of h can be written in cylindrical components as follows. So curl of h is equal to 1 over rho partial z over partial phi minus partial h phi over partial z a rho minus this term plus this term. So this is actually the curl of h in cylindrical components, and this is the expression for curl of magnetic field intensity in spherical coordinate system. So that is all about our today's lecture, and I hope you have understood the concept discussed in this video. For watching more lectures, please subscribe this channel. Until the next lecture, it's goodbye.